Hello, can you hear me? Hello.
Hello?
Y-
Hello?
Yeah, you can hear me, right?
Yes.
Okay, so we'll continue with Ivan Chen textbook and we'll look at
Okay.
section 1.2. Okay, so
Okay.
that is about cyclic quadrilaterals. Have
Okay.
you had a chance to read any of it?
No, I haven't really. I was busy with exams.
Okay, so last class we talked about cyclic quadrilaterals. We said that any quadrilateral, all the vertices, all the four vertices lie on a circle, right? Lie
Yes.
on a circle, then that quadrilateral is called cyclic, right?
Okay. Right?
And if I draw a circle like this, let's say, and we draw a quadrilateral inside. So A, B, C, D. And let's say the center is somewhere here, O. Now, this ABCD quadrilateral is a cyclic quadrilateral, and we can prove that by inscribed angle theorem, you will be able to prove that this angle plus this angle, angle B plus angle D, will always be 180 degree. And similarly, angle
Okay.
A plus angle C will always be 180 degree. So
Okay.
basically, in a cyclic quadrilateral, you can say that the opposite angles are supplementary, right?
Okay. Yeah.
How do we prove that? What we can do is, let's join this roughly like this and this like this, and we will look at the arc ABC. Arc ABC. Can you see this arc? This one.
Yeah.
So that arc is making an angle at the center, right? This angle, right?
Yeah.
So basically we say that the measure of this arc is angle at the center that is made by that arc, which is angle AOC, right?
Yeah.
And by inscribed angle theorem, we know that the arc will make another angle at a point on the circle. The same arc ABC makes angle ADC on the circle, right?
Okay. Right.
You can see that, right?
Yeah.
So by inscribed angle theorem, we know that AOC will be 2 times of ADC, right?
Right.
So angle at the center is double of the angle at the circumference, correct?
Correct.
So if this angle is x, this angle is 2x, right?
Right.
And now look at arc ADC. The arc ADC is this arc on the other side. That arc makes this angle on the center, right? This angle.
Yeah.
And it makes this angle on the circumference. It makes angle ABC on the circumference, correct?
Yeah.
So if this is y, then this is 2y, right? By the same principle, inscribed angle theorem.
Yes.
So now angle AOC plus angle, let's not call it AOC because AOC will stand for both of these. We'll say that this is 2y and this is 2x. So 2x plus 2y should be equal to 360 degree, right? Because it is
Yeah.
the total angle around the point O, right? Correct.
Correct.
So therefore x plus y becomes 180 degree, right?
Yeah.
So x plus y is 180 degrees. So we have proved that the opposite angles add up to 180 degrees, right?
Yes.
We can do the same thing for this angle and this angle also. Then we will have to join B to O and D to O and take these, right? These and this.
Yes.
So basically, the first thing that you have to understand is when opposite angles of a quadrilateral add up to 180 degree, the quadrilateral is a cyclic quadrilateral. Okay.
Okay.
So that is our first thing. If opposite angles add to 180 degree, the quadrilateral is cyclic. And by cyclic, I
Okay.
mean that all four vertices lie on a circle, right?
Right.
Then we look at proposition 1.8. So proposition 1.8 in the book. So in that proposition, he tells one more thing. He says the supplementary opposite angle stuff, but he says one more thing, the second part of it. So let's say we have A, B, C, D. So of course, this quadrilateral is cyclic. Therefore, angle DAB plus angle DCB is equal to 180 degree, and also angle ADC plus angle ABC is also 180 degrees. But apart
Okay.
from that, we can also say another thing. So what is he saying in this proposition? He's saying angle ABD is equal to angle ACD. Angle ABD is equal to angle ACD. So what does that mean? Let's draw a line like this. So that will become your ABD angle, and ACD will
Okay.
draw a line like this. And this is your ACD angle. Can you tell me why these two angles have to be same?
Um, they have to be same because
Because it's the same arc, right?
yeah, it's on the same arc.
It's the same arc AD that makes this angle here on a point, and it is making the same. It's making another angle on another point of the circle, right? So
Right.
if they have the same arc, then they will have same angles at the circumference, and both of these angles will be called, let's say, x and x. Then the angle at the center will be 2x, right?
Yeah.
If this
Right.
is the center, this angle will be 2x. Does that make sense?
Yes.
So this is very important to know, because sometimes in problems they will not even give you a circle. They will just tell you some
Um.
information. Like for example, they can show you a quadrilateral like this and tell you that this angle is matching this angle. Okay.
Um.
And then
Okay.
the circle is not even part of the question, but you can immediately say that this quadrilateral is cyclic.
Let's see.
Why? Because this angle is matching this angle. So you can imagine a circle and say that, okay, due to the arc AB, equal angles are being made on C and D, right?
Right.
Are you understanding what I'm saying?
Yes.
So just this fact that these two angles are matching makes the quadrilateral cyclic. And if it is
Okay.
cyclic, we can say many other things also. Now we can say that this angle will also match this angle, right?
Right.
Why? Because it is due to arc CD, this arc,
Yes.
right? And we can also say that this plus this should be 180, and this plus this should be 180, right?
Okay.
So
Right.
none of the circle part need to be mentioned in the question. It can look like a question that is about quadrilaterals and not about circles, but you will still end up getting
Yes.
all of that stuff just by knowing that angle ADB is equal to angle ACB. So that is enough for you to tell that it is cyclic, right?
Okay.
So that is
Yes.
very important. Listen, see what he says. Uh, okay, theorem 1.9, he is talking about the same thing. He's just writing it properly. He's saying let ABCD be a convex quadrilateral. Then the following
Okay.
are equivalent. The following statements are equivalent, which means that if any one of them is true, the other ones are also true, right?
Okay.
So
Right.
First statement is ABCD is a cyclic quadrilateral, and then that means that the opposite angles add up to 180 degree, and that also means that angle ABD is equal to angle ACD, right?
Right.
Now look at question example 1.1. If you see example 1.1
Okay.
earlier, he had given that question, right? We had solved that question by a different method, by congruency and similarity, if you remember, right?
Yes.
Angle X was difficult to find, right? Last class we discussed that, correct?
Yeah.
But
Correct.
now look at it again. Uh, what is given has been drawn in figure 1.2b, okay? And the figure is like this. Okay, so we'll say WXYZ WXYZ, and we will draw the figure. The line WY and XZ are perpendicular to each other. WY
Okay.
and XZ are perpendicular to each other, right? And some angles are
Yeah.
given to us: 40, 30, 40, and 50. So here this is 40, this is 30, this is 40, and this is 50, right?
Yeah.
Now, earlier in the previous class, we did it by congruency and similarity. Our job is to find angle X, right?
Right.
But now we can do it by cyclic quadrilaterals, because notice that this angle is 40 and this angle is 40, right?
Yes.
And it is subtended by the same chord, this chord, right?
Right.
So you can imagine a circle that passes through WXYZ, and arc XY is subtending 40 degree and 40 degree, right?
Yeah.
So this quadrilateral becomes cyclic, correct?
Yeah.
Because of the fact that angle XWY is same as angle XZY is equal to 40 degree. Therefore, WXYZ is cyclic, right?
Yeah.
And as soon as it is cyclic, this angle is 70. So angle X has to be 110.
Yeah.
You understand, it's a two-step problem if you realize that it is cyclic.
Okay.
In the earlier previous class when we did, we had to prove similarity, congruence of this, and or similarity of this, and then similarity of this, and then finally we got it, right?
Yes.
So that is much longer, but if you know the cyclic quadrilateral stuff, it becomes much faster, right?
Yeah. Right.
And see what he says at the end. He says, in some ways, the solution is totally unexpected. Nowhere in the problem did the problem mention a circle. Nowhere in the
Yeah.
solution does the center ever appear. We don't have to draw the circle and all. We just have to say that it is a cyclic quadrilateral, right?
Yes. Right.
And yet, using the notion of a cyclic quadrilateral reduced the problem to a mere calculation, whereas earlier it
Yeah.
was a little difficult, right? So he's saying now we stress the importance of theorem 1.9. Theorem 1.9 that we just now saw. That theorem is super important. It is not an exaggeration to say that more than 50% of standard Olympiad geometry problems use it as an intermediate step.
Okay.
Basically, all the geometry problems that you will encounter in all Olympiads, most of them will use somewhere cyclic quadrilateral theorem 1.9. Okay. So that is a very common thing. So you need to understand that. All the three parts of it, right?
Okay.
Is it clear?
Yeah.
Okay, so now try problem 1.10. Problem
Okay.
1.10, which says, show that a trapezoid is cyclic if and only if it is isosceles. Show that a trapezoid is cyclic if and only if it is isosceles. So
Okay.
whenever there is an if and only if statement, we have to prove both sides, right?
Right.
And do you know what is the meaning of a trapezoid or trapezium?
Yeah.
What is it?
Isn't it almost like a triangle, but like the top bit cut off?
That's correct. But the way you say it is, it's a quadrilateral with one pair of parallel sides.
Okay.
Like it's a quadrilateral where one pair of sides is parallel. If two pairs of sides become parallel, it becomes parallelogram, right?
Yeah.
Like this is a parallelogram where these are parallel and this is also parallel, right? A
Right.
trapezium is when these two are not parallel, like this and this are not parallel necessarily.
Yes.
So only one is parallel. So the question is asking you to show that if you have a trapezium which is cyclic, then it is isosceles. Isosceles means two sides must be same, right? So
Yeah.
first part of the problem, you should say that a trapezium is cyclic. That can be assumed, and from there we have to prove that it is isosceles.
Yes.
So we can draw a circle and we can draw a trapezium in that circle. Let's say like this, right?
Right.
So basically this is parallel to this and all the points are on a circle. So it is cyclic quadrilateral, right?
Right.
And now you have to somehow prove that it is isosceles. Isosceles means proving that AD equal to BC. So think of how to do that.
Okay. Mm. Well,
You don't have to
probably
immediately.
because
Okay, think about it and make sure that you get it. You don't have to say the
okay.
answer immediately.
Hmm.
So what are you thinking about? What are your thoughts?
So the first thing I'm thinking is drawing in the diagonals probably.
Mm-hmm.
Um, then if it were to be equal,
No, that you can't assume. You have to
oh,
prove that. You have to assume that it is cyclic, which we have assumed by drawing it on a circle. You have to prove that it is equal or AD equal to BC or something. You have to prove.
okay.
What you should
So
do, think about the angles.
okay,
If this angle is X, What is this angle?
So that then surely B is also X
No. Why should it be X?
because oh no, if that angle is X,
It's a cyclic
uh,
quadrilateral. Cyclic quadrilateral. Opposite
yeah,
angles will be what?
equal. So that's also X. C is also X.
Why will opposite angles be equal?
I mean, not equal. Then C will be
Sum of opposite angles in a cyclic
180
quadrilateral.
minus X.
Yes.
I mean,
Why,
yeah.
why are you saying equal?
Oops, I
So this is 180
accidentally
minus
said something.
X.
Okay.
And if it is a trapezium, you already know that this is parallel to this,
Yes.
right? So if these lines AB is parallel to CD and this angle is 180 minus X, what is this angle?
Um. Well, you know that that angle would be.
Parallel
Oh,
lines.
that angle would just be X.
Yes. And what will be this angle? If this
Oh,
line and this line are parallel.
that would be 180 minus X.
So now you are getting that this angle is equal to this angle, right?
Yeah.
So that and this angle is equal to this angle, right?
Yeah.
Then you can say that the trapezium is isosceles. It's like a situation like this. All the angles are matching, right? This angle is matching this angle. This angle is matching this angle, right? Why is this an
Yeah.
isosceles? Why is it called isosceles? Because you can imagine a further line like this. If base angles are equal, then the whole triangle would have been isosceles, right?
Oh, yeah.
And then since these two are also equal, this is also equal to this, right?
Right.
Correct. So this
Correct.
side would also be equal to this side, right? For the imaginary top part of the triangle, right?
Right.
You understand that this would have been equal to this?
Yes.
And the whole thing is also equal, right? Because the big triangle is
Yeah.
also isosceles. So that means that the difference is equal to this, right?
Right.
So basically AD is equal to BC comes if you have base angles same, right?
Yes.
So that is your isosceles trapezium. AD becomes equal to
Mm,
BC. How is it?
okay.
How is it coming? First of all, we called this angle X because it is cyclic quadrilateral. This became 180 minus X. And because these are parallel lines AB and CD, here 180 minus X, so opposite interior angle is going to be X, right?
Oh, yeah.
Because of parallel lines, right?
Yeah.
And similarly, if
Right.
here is X, it will be 180 minus X here, right?
Yeah.
So now the
Right.
trapezium is such that the base angles are equal and the top angles are also equal. So the side will be equal, the non-parallel side. AD will be equal to BC.
Yes.
Do you understand why AD is equal to BC?
Yeah.
Why?
Well, AB will be equal to. I mean, AD will equal to B because then surely because AB can't be equal to DC as to make the isosceles triangle. Um,
Suppose
you'd
we
almost
have,
need like a similarity where the
you need to properly explain. Like, so let's say this angle is equal to this angle and this angle is equal to this angle.
Yeah.
How will you prove that AD equal to BC? Prove.
Um. Well, you can prove it by. Let me think.
That's what I was explaining by extending this,
Yeah.
right? Extend
Yeah.
it, call this.
Yeah. So if you so basically, if you extend it, makes an
Hmm.
isosceles triangle.
Why is the
Basically,
triangle
you can
isosceles? Because this is
because
equal to this.
yeah. So the triangle is isosceles,
So,
and this small triangle is similar to the whole big triangle.
so you get FD equal to FC, right? First of all.
Yeah.
And this angle is also equal to this angle. So this is also equal to this, right? And you get
Right.
FA is equal to FB also, right? That small triangle is also isosceles, right?
Yes. Right.
So AD is what? AD is the difference of FD minus FA, right?
Yeah.
And BC is FC minus FB.
Uh,
So those will also be equal to, no?
right.
Are you sure you understand?
Yes, I understand.
So that is the first part we have done. When we said that the quadrilateral was the trapezium was cyclic, and we proved that the trapezium has to be isosceles. Now we have, if there is an isosceles trapezium,
Okay.
if there is an isosceles trapezium, prove that it is cyclic.
Uh,
Prove that it
then,
is cyclic.
well, since it's isosceles trapezium,
Hmm.
we already know that truly angle BCD and ADC we know are equal.
Hmm. This is
So
X,
that's
this
what
is
we have.
X. Hmm.
And then,
And then AB is parallel to this, right?
yes.
Because it's
And
a
since they are
trapezium.
parallel, you can use cooperating
Hmm.
angles to know that's 180 minus x, and b is also 180 minus x by cooperating angles.
Hmm.
And then with that, it's cyclic, I'm pretty sure.
But
Since
why?
opposite angles add to 180.
It is cyclic because angle A plus angle C adds to 180,
Yeah,
right? So we have
right.
proved now both sides. So that completes the question. Are you
Yeah,
understanding?
right.
Okay. Then try question 1.11.
Okay.
Okay, I will not say anything. Try yourself. Quadrilateral ABCD quadrilateral ABCD has angle ABC is equal to ADC is equal to 90. ABC is equal to angle ADC is equal to 90 degree, and show that ABCD is cyclic. Show that
Okay, so
ABCD is cyclic, and also and that circumcircle of ABCD has diameter AC, and circumcircle of ABCD has diameter AC.
he, mm, Well, surely it's cyclic because opposite angles add to
So you have
180, so that means it's
so you have angle B plus angle D is 90 given, 90 plus 90, 180. So therefore
yeah,
quadrilateral is cyclic.
yes.
Now you have okay, now there must be some circle like this then which passes through all the four vertices, right?
Yeah.
So we have to prove that the circle has diameter AC. So if I join AC, AC is a diameter, we have to prove.
Well, then surely, oh, okay, so you have to prove that goes through the center.
Center is on AC basically.
Yeah,
We have to prove that.
well, hmm, well,
This is a type of question that we did in the last class. One of the questions had an idea like this only. So
yeah,
you can, if you have to prove that the center is on AC, you can first assume that it is not on AC, right? Let's assume
okay,
that it is somewhere else, right? Center of the circle
yeah,
could be somewhere else. Let's call it O dash, right?
G,
Now, if it is at O dash, think of the arc ADC, right?
right,
Now, this arc ADC is making what angle at the point on the circle, B point? It is making
it's
90
making
degree.
yes,
So angle on the circle that it makes is 90 degree. So what angle should it make on the center?
oh, and 180 degree.
So right
So
now
it
if
should make
I
twice the amount.
twice the amount. So right now if I join the A point to the center and C point to the center, this angle should be 180 degree, right?
Yeah,
But if this angle is 180 degree, it's a straight line, right?
yes,
So if it's a straight line, then O dash lies on AC, right?
yeah, I see.
It can't be a straight line. It can't be 180 degree if it is not on the line AC, right?
All right,
You understand?
yes,
So the center is on AC, and if center is on AC, then AC is a diameter.
okay,
By the way, you should know that angle in a semicircle is always 90 degree. So for example, if I have a circle like this, and let's say this is AB, this is the diameter O. Now, if I use this arc AB, the chord AB, and I
okay,
make any angle like this on any point inside on the circle, right?
right,
Let's say this is D, this is E, this is F. All of these angles are 90.
uh,
Why? Same logic, because it is arc, the chord is going to make equal angles on all the points on the circle, right?
okay,
And this angle is 180, right?
yeah,
So the arc AB, if you think about it, is making 180 at the center. So it is going to make 90 here, 90 here, 90 here, right?
right,
Are you understanding?
Yes.
So if you have a semicircle, AB is a diameter, then if you take AB as the chord and from there you make angles on a semicircle, all angles will be 90. This is 90, this is 90 and all. Right?
G.
So that
Right.
is what is happening here. It was like this, like this, like this, and this was 90, this was 90, so the quadrilateral was cyclic. And once it became cyclic, then this is 90-degree angle and this is a point on the circle, so this must be diameter.
G.
Because diameter will make 90-degree points on the circle, right?
Yeah.
Are you understanding?
Yeah.
Okay. Uh,
Yes.
then we look at 1.3, which talks about the orthic triangle. So that is a very
Okay.
important concept. 1.3. Here we draw a triangle ABC and we draw the altitudes of the triangle, the three altitudes of the triangle. So what do we mean by
Okay.
altitudes? Altitudes
Uh,
means what?
it
Point,
means the lines. The
line
lines looks
from
like which.
vertex to the opposite
Yeah.
side, right? And which
Yes.
is perpendicular, right?
Right.
So from A, I can make a height. It's like this, right?
Yeah.
This is AD is an altitude. Similarly, I can make an altitude from here. This is BE. And
Yeah.
there is one more that you can draw like this from C to the opposite side. And this is F, right?
Yes.
Now, if I tentatively join DEF, right?
Right.
Like this. If I join DEF, the triangle DEF is known as the orthic triangle.
Okay.
Orthic triangle. And the point where the three altitudes intersect is known as the orthocenter H. So point of intersection of altitudes is called orthocenter.
Okay.
Okay. Is H or orthocenter. You have not done this before, right?
We did go through it.
In school, you have seen this before.
No, I've done it. I went through it with you.
Okay. Okay. So what we want to understand here is in this figure, can you spot some cyclic quadrilaterals? Can you find some cyclic quadrilaterals?
Um.
In this whole figure, you have to think about some cyclic quadrilaterals.
Yeah. Surely
There are many.
would.
Look at HDCE.
HDCE. Okay.
Is
Oh
it
yeah.
cyclic? Because
Um.
90 and 90, right?
Yeah.
And similarly, look at HDBF.
Okay. Yeah.
HDBF is also cyclic because 90 and 90. Opposite is adding up to 180, right?
Right.
And similarly, HFAE.
Yes.
That also by the same logic, right?
Right.
That is also cyclic, na?
Yeah.
Okay. Now, there are more, but for now, this will be enough for us. What we will look at
Okay.
are certain properties of these quadrilaterals.
Okay.
Okay, so because look at HDCE. If HDCE is a
Okay.
cyclic quadrilateral, what will be
Yeah.
the value of this angle? This angle will be equal to this angle, right?
Yeah.
Why?
Um.
HDCE is cyclic. So HE
Yeah.
will be some arc, right? From the chord HE, you are making
Yeah.
an angle here. That should be the same angle that the chord HE makes here, right?
Yes.
You don't understand. Do you
Yeah. Not
understand?
really. Kind of. Not really.
Okay, so we'll draw the HDCE separately. Let's
Okay.
say like this, right? This is H,
Okay.
this is E, this is D, this is C. We know that it is cyclic because of these two 90 degrees, right?
Right.
So let's make the circle. Make the circle
Okay.
like this. Circle should pass through all of the vertices, right?
Right.
Now think about the third property in your theorem 1.9. Look at the third thing in theorem 1.9. What was it
Okay.
saying? If it is cyclic quadrilateral, this angle should match this angle, right?
Yes.
Are you understanding why this and this angles are same?
Yeah.
Why?
Um, the angles are the same because um, surely that the angles are just both almost, because angle D, HTC and HEC are equal,
Oh, that's
then
fine, but that doesn't affect this angle and this angle.
uh
It,
uh
it is coming from
well,
circle properties. Circle, think of the circle. In the circle, what is the arc HE?
oh, that's like,
This arc is making an angle here, right?
yes.
The same arc is making an angle here.
Oh, yeah.
So that's why the angles
So
are
the
equal.
arcs, okay,
Are
the
you
arcs making two the
understanding?
same angles. Yes, I'm understanding now.
Because there is a circle, because it is cyclic, there is a circle. And because there is a circle, there is a common arc, this arc, which makes
Okay,
an angle here and it makes an angle here. Both angles will
understand.
be matching because the arc is the same, right?
Right.
So here, if you forget about the circle for a minute, what is this angle in terms of the triangle? This angle.
Um, that angle will be,
Think of this 90 degree. This is
oh,
90, this is something, and this is angle A, right?
so that will be 90 minus A.
So this is 90 minus A, right?
Yeah.
And so this also is now 90 minus A, right?
Yes. Right.
And now similarly, if you look at quadrilateral HDBF, That is also cyclic, right?
Oh yeah.
That is also cyclic
Cyclic.
because of 90 degree, 90 degree, right?
Yeah.
And can
Right.
you say that angle, the again, imagine in your head a circle like this passing through the 4 points, right?
Yeah.
And then this angle should match this angle, right? Because of
Yes.
this arc.
Yeah.
Are you understanding what I'm saying?
Yes.
So you'll have this angle FDH. This angle FDH will be equal to FBH, right?
Right.
Are you sure you are understanding?
Yes.
Same principle because it's cyclic and there is an arc that is common arc HF, right?
Right.
So now what is this FBH angle? FBH angle can you find from the triangle? This is 90 degree
Yeah.
and this is angle A. So FBH is how much?
Um. FB A. That would eventually that would be also 90 minus A.
It is also 90 minus A, right? So if this is
Yeah.
90 minus A, then this is also 90 minus A, right?
Yeah.
Correct.
Correct.
So this part is 90 minus A, this part is 90 minus A. So total angle FDE is equal to 180 minus 2A, right?
Yes.
Is it clear?
Right. F. Yeah.
FDE, the whole thing.
Yeah. Yeah.
We saw the two parts, we proved it in 90 minus A, 90 minus A. So the total thing is 180 minus 2A, right?
Yeah.
You can do the same
Right.
exact same proof for all of these angles. This angle, and this angle,
Okay.
and this angle. It will come that this angle will be 90 minus B, 90 minus B. So this angle total would be 180 minus 2B. And this will be 90 minus C, 90 minus C. Same thing you have to do. And you will get 180
Okay.
minus 2C here, right?
Right.
So now what we have gotten is all the angles of the orthic triangle. Triangle DEF,
Um.
all the angles are 180 minus 2A, 180 minus 2B, 180 minus 2C, right?
Yeah. Right.
And if you add up all of them, you can see that it will be 540 minus 2 times A plus B plus C, and A plus B plus C is 180. So it is 540 minus
Yes.
360, which is 180.
Right.
So that makes sense, correct?
Correct.
So now, so far what we have done is we have gotten everything, every angle in the orthic triangle. So A, B, C. First we drew one perpendicular like this, one perpendicular like this, and one perpendicular like this. And this point became H. This is D, this is E, this is F. And then we joined this, we joined this, and we joined this, right?
Right.
And now we know all of these angles, this angle, and so on, right? All of these.
Yes.
So the total angle here is 180 minus 2B. The total angle here is 180 minus 2A. And the total angle here is 180 minus 2C, right?
Yeah. Right.
We also know, by the way, all of these angles because this
Um.
angle will be 90 minus A and this angle will be 90 minus C. Do you understand
Yeah.
why?
Um.
If you look
Mhm.
at triangle ABE, this is 90 So this must be 90 minus A, right? This portion.
Yeah.
Because this is angle A. And if you look
Yes.
at triangle BEC, right? This is
Yeah.
angle C and this is 90. So this must be 90 minus C, right?
Uh, right.
Makes sense, right?
Yes.
Okay. Now we will try and find some other cyclic quadrilaterals in this figure. So
Okay.
let's look at the quadrilateral. Uh, let's find this angle. What is this angle?
Um.
This angle would be uh, this is
Hmm.
C, right? And
Yeah.
this part was 90 minus B, this part, right?
Yes. So then.
So this angle is B, right?
Yeah. Yeah.
Are you understanding why? Because
Yes. Yes.
angle,
Yes. Cause
okay, angle BEC is 90, right? And
yes.
angle BED was 90 minus B, right?
Yeah.
So angle DEC is B, right? So if this is B, this is C, what is this angle? It is 180 minus B minus C, right?
Right.
So 180 minus B minus C is actually A, right?
Yeah.
Correct, no?
Correct.
So now
Yeah.
think about it. What is angle FDC? What is FDC?
Um.
FDC should be equal to 180 minus 2A plus A, right?
Yeah.
Because this part was coming as 180 minus 2A, right?
Yeah.
So FDC is equal to 180 minus A, right?
Um. Yeah. Right.
And now look at quadrilateral
Okay.
FDCA.
Yeah.
FDCA, right?
Yes.
So in that, this angle is A and this angle is 180 minus A.
Uh.
So this is cyclic, right?
Yeah.
Do you understand why it is cyclic?
Yes.
Okay, so we got FDCA is cyclic. So similarly, we should get BDEA is also cyclic. BDEA.
Yes.
Why? Again, we will do the
Oh.
same thing. We will
Yeah.
now we will now say, okay, if this angle was A, the EDC angle is A, so BDE angle is 180 minus A, right?
Yes.
And this is A. So BDEA, this is adding up to 180, opposite angles, right?
Right.
So two more we are getting FDCA, BDEA, and and BDEA, and similarly we'll get CF, FECD, right?
Right.
Because of the symmetry, that also will come as cyclic. Notice that
Okay.
when we did FDCA, we took one side of the orthic triangle, and FD
Yeah.
was this, and then CA was this one. And when we took BDEA, we took the other side, DE here and AB here, right?
Yes.
So now we'll take EF here and not CD, I think EFBC.
Ooh. Okay.
Mm, maybe we'll check. FECD, let's check. Uh,
Okay.
whether FECD is cyclic or not. So we already know this overall angle is equal to 90 plus 90 minus A, right?
Right.
Because this part is 90 minus A and this part was 90, right?
Yeah.
So it is 180 minus A, and
Yeah.
in FECD, this part is becoming 90 plus 90 minus B. So it is 180 minus B, right?
Yes.
So that is not 180, right?
Oh, yeah.
So FECD is
Right.
not cyclic. So
Okay.
FEBD I think will be cyclic, because
Yeah.
if I take FEBD, I would get 90 plus 90 minus B here. So it will be 180 minus B angle on this side, and this angle was 180 minus A. Oh, that is also
Yeah.
not coming as cyclic. I'm missing out on one cyclic quadrilateral. FDCA was coming, and BDEA is coming.
Yeah.
DCFA, FACD. Look at that one. FACD. So,
Okay.
okay, that already we got. Basically,
Oh, yeah.
there is one more. We are missing it right now, but don't worry about that. You could try to find it. But do you understand the whole point of how you get cyclic
Yeah.
quadrilaterals? Right?
Yes, I understand.
Go through the go through the examples here. Example 1.13 onwards.
Okay.
1.13, and then there is lemma 1.14, and then there are some problems 1.15, 1.16, and so on. Right? So try all that.
Right.
We will be discussing that in tomorrow's class. So make
Okay.
sure that you start doing all of this. Try all that. We'll discuss this, continue from this point. Okay.
Okay.
Okay. That's all for
Bye.
now. Bye.